Welcome back. It's been a couple of weeks. Um, yeah, as I mentioned in my last video, I we were expecting the birth of my son, and he is here. Um, yeah, he was born. Mom and baby are doing great. Um, yeah, it's been a crazy time. Just what a yeah crazy life event. Some sleepless nights, but we're doing okay. Doing pretty good. Um, anyway, so I have a little bit of downtime, so I figured I would maybe record a follow-up video um, just to kind of explain how I built chess. So for those of you who haven't seen it, my previous video is I built a chess computer in Minecraft. So here you see it's just a 3 by 3, but it scales all the way to an 8 by 8 board. So if you haven't seen that, check it out. I show some of the functionality, and I show a game as well. Um, but yeah, I um, thought I would record a follow-up video and just explain a little bit of how I built this machine and how everything works. Um, yeah, I thank you for the comments. I really appreciate all the feedback and all the comments. They were overwhelmingly positive and yeah, really encouraging. It's just great to see people enjoy this kind of build, and yeah, it makes me want to keep building and um, yeah, and also record and share. So I really appreciate that. Uh, Several people did ask for a little bit more of an explainer video, so that's what this will be. So I apologies in advance. This is going to be a little bit more of a talky video, just kind of walking through how this whole thing works and what it does and how it, yeah, maybe some of the interesting things I had to figure out along the way. Um, but if that's not your thing, then no worries. Have I'm already working on my next project. So I have another idea, which I think is pretty cool. I'm in the testing phase right now, just to see if I can make it work, if it's feasible. But it's another idea that I want to build. It's another pretty big project, just with vanilla redstone. And yeah, I think if I can get it working, it'll be pretty cool. I've never seen anyone do anything like it, and so yeah, at least when I was searching, I wasn't able to find anything like this that I'm hoping to build. So yeah, so be on the lookout for that. Hopefully that'll be, I've got a little bit of time. So hopefully that'll be in the next couple of months, if I can get it. Yeah, if I can get it all working. Um, but yeah, for now, this video I just wanted to make, yeah, just to talk about how the chess computer works. In order to do that, I made this rudimentary flowchart here, which um, is just kind of the logic of how the machine works and all of the steps along the way. So I think I will use this flowchart as I talk through the different stages for this video, and it'll just make it a little bit easier to follow, hopefully. And I'll highlight any interesting things that I found, interesting workarounds or ways to build certain things. Yeah, as I go. So, uh, yeah, so I hope you guys enjoy. Let us dive into it. Okay, so what we are going to do is follow one move um, that the machine does when we push a button. So we will start by pushing this button to move white, and white should move randomly because one of the checks is, even though the rook can take the knight here, it would be in danger by the other rook, and white's rook is of lower value than black's knight, so it will not take here. Instead, it should do a random move. So we're going to move for white, and it's going to check where it should move. All right, and it has made a decision, and it is moving the knight either here or here. Okay, and it moves up here. So let's follow the logic and see what the machine did. So we push a button and we check whose move it is. In this case, it's white's move. So we prime the active black pieces. What that means is we push the button. The first piece is pretty straightforward. It goes down here into a bit of a section that just alternates between white and black, depending on whose move it is. And it sends a pulse over to this side of the machine here to see where black's pieces are, to see if any of black's pieces can be captured. So if we zoom out for a second, the way this machine is built is the right side here stores black's pieces, and then the left side stores white's pieces. And then all of this down here is essentially data for how to do piston changes, piston sequences, in order to switch one piece on a square from one piece to another. So we'll get to that a little bit later, but yeah, so the black pieces are stored here. The white pieces, the locations of the white pieces are stored here. And then there's a bunch of logic that's built into these so that I can do various checks. So the first thing that happens is a pulse gets sent through the black side, the black tower here, and it wants to see where black's pieces are. And so what this primer does here is it resets to see where any active pieces or where any pieces currently are on the board. And so essentially primes the pump for this next step, which then pulses through all of the pieces from highest to lowest value to see which piece it can take. So it primes it, and then I send a zero tick pulse. The way I built it here, I wanted the zero tick pulse to either activate a piece and then basically log whether it's been activated or checked, or activate the next piece. And so what that means is where you see the blue wall here, you'll notice it's all on that side right now because it is not primed. And then once it is primed, it actually changes this wall to highlight which pieces are active. So the lowest value here, or sorry, the first piece that it checks is the king. So you can see all of these are basically horizontal like sections. And as we work our way up the tower, the pieces go from most valuable to least valuable. So if there's a king on the board, the first piece it will try to capture is the king. And then it kind of iterates through all of the pieces going up, and if it cannot capture that piece. So in our case, it went up to the rook and then the knight, and it realized that neither of them were capturable. And so then it went all the way up to the top and did a random move instead. So we pulse the next piece to check, and then we send a move command to the white side and basically find the destination square where we need to move to. So it pulsed up, found that there was a rook. That was the highest value piece, the first highest value piece that it could check. and then it sent that information over to the white side of the board, and the information it sent was basically move to this destination square. It then checks all white pieces that can possibly move to that destination square, and it accounts for valid piece moves and collision detection at that time. And so the way I did that is I decided that the fastest way to build this would be to have one tower or one check for every source to destination. In other words, in this setup here, there's 9 squares. And so we have 9 times 9, so 81 possible permutations, where 9 of those are discarded immediately. So we have 81 source destination permutations. 9 are discarded immediately because source destination being the same square doesn't get checked. And then I scripted out a way to actually check what all valid moves are for every single piece type from every source square to every destination square. So when it moved the knight here, for instance, it it knows that the only 2 valid knight moves from this square are this square and this square. And so since I laid it out this way, it also allowed me to build in collision detection for every source to destination permutation. So for instance, for the queen checks for this square, this source square and this destination square, I could put in this square as a collision detection check. In other words, if there's any piece on this square, regardless of the color, then a queen move from here to here becomes invalid. And scaling that is actually quite straightforward to an 8x8 board, because once I have that, I can essentially do 4 different kinds of, or 4 different directions of collision detection tests. So in this case, this is just a 3x3, but imagine that this board extended outward and we take this middle square here. Then for a queen move, the queen can move horizontally, vertically, and diagonally. And so what I do is I check collision on the horizontal, I check collision on the vertical, and then I check collision on each of the diagonals from the source square. And that gives me a pretty straightforward way of building something that can find any collision that happens from the source outward towards the destination square. So let's take a quick look at what these towers look like. So as I mentioned in the previous video, the way I built this whole thing was procedurally, and I did that just because there were so many different components that had to be connected in a certain way, precisely in a certain way, especially with the scaling, that this just made my job a lot easier to actually easily build this, make changes, rebuild it, etc. So what you're looking at here are the towers, or the components of the towers that do the piece move logic as well as collision detection checks. And these towers took a while to design. I went through several different iterations of this. And I won't explain everything in detail here, but essentially by stacking these towers and then scaling them outward horizontally in both directions, it allows me to make a volume space of X and Y coordinates that serve as source and destination. And the Z axis, or the vertical axis, I can then layer on top every single piece that needs to do this kind of check. So if we look at the machine and see what this looks like, and it's a little bit difficult to see here, but you'll notice, for instance, the purple here, the purple wool, these are the collision detection in the 4 different directions. So vertical, horizontal, and 2 diagonals for the queen. So the collision detection happens below the actual piece. So you'll see this light blue wool here is where the king check is. The king doesn't require collision detection because it only moves 1 square. The queen requires the most because it can move vertically, horizontally, and diagonally. And so then everywhere where you see a light blue line, behind that line is essentially a plane in which my source and destination squares can actually check to see whether they can get to the end. So it's a little bit difficult to explain, but let's say I want to move from 1 to 2, then, so square 1 to square 2, then this first line here would be the source square, and the destination square will then be whether I can move to 2 is then factored into the destination line and comes out at the other end here. And I prime the destination line at the very bottom. And so if we go back to this here for a second, we find the destination square first, and then the priming of that destination square happens vertically at the very bottom, and essentially sends a signal up to all of these different planes. And so this entire volume here, this whole volume, which extends in the other direction, serves as the primary logic for validating what valid piece moves are. And that takes into account, the collision detection. So we send the destination square up, then we have power to the source square over here. This gets pulsed a little bit later on the logic. And if the destination square and the source square are a valid piece move, taking into account collision detection, then we get a pulse coming out at the end here. It does this simultaneously for all valid piece moves, or for all pieces that can possibly move to that destination. And so my check is actually, like, I ask the question in reverse. I don't say, where can I move to? I say, who can move to the square that the king is on, the square that the queen is on, and so on. And that allows me to do a little bit better than random or greedy AI, because essentially I get information out the back of this unit on these different levels that tell me which pieces can move to the destination square that I've asked the question for. And I can then manipulate or decide on which piece actually moves to the destination square. And what I decided was to essentially move the piece of lowest value to the destination square at all times. So at this point here, we have a bunch of lines going out this way by the green here. And this information goes this direction. And we have this control tower in this corner of the space. This control tower here will take as input all pieces that can move to the destination we requested, and then send as output only one source square. And the two variables it takes into account, or the two rules, are it will move the lowest value piece that it can to the destination square. But if it's taking a piece, it will actually only take that piece if the piece it's taking is of equal and or greater value, when that piece will be in danger after the move completes. So the reason the rook here didn't take the knight is the knight is worth less, so the knight appears higher on this chain, and the rook knows that this square would have been capturable by black. And so there's a lot of like stateful information being passed between these modules. I tried to build as much as possible, essentially not with a clock, but with stateful data. So stateful data lines, basically that information is constantly held, or power is held to the lines when something is true. And so right now, both sides of the system know which squares are capturable by the other color. And so that allows me to essentially do checks along the way as I'm making my decision on which piece to move, that can be asynchronous, and I don't have to run this entire thing on a clock. Running it on a clock would have slowed it down, because it naturally leads towards more serialization. B, it would have added to the complexity, because now you're dealing with a lot of timings that you carefully have to manage. And C, it would have made scaling it much more difficult, because when you're running things on clocks and you're scaling, by the nature of things becoming serialized instead of parallelized, you have to account for the added delay as the machine gets bigger. And so instead, I tried to build most of these like cross-component checks with instant wire, as well as stateful. And so this allowed me to scale it in a way that I didn't have to account so much for delays that came from adding more components. Because I mentioned before that this thing is 9 by 9, like has 9 by 9 checks, so 81. So at 64, at 8 by 8, we are at an 8 by 8 square board, we have 64 squares. And so we now are 64 times 64 wide. And this is the reason that the machine scales to be so big, is because 64 times 64 is 4,000. And so 4,000 lines, essentially, or horizontal slices, so that I can check every source destination square combo. Okay, so one check it does is it checks to see whether the destination square is in danger before it makes a move. The other check is whether the piece it wants to move is the lowest value piece that it has. And based on those two checks, it then makes a move. And once again, back to this like control tower here. This control tower will then send out a pulse along these lines. And this is the pulse that is the source square pulse. So it will either take the piece in question, regardless of the value difference between these two pieces. if this square is not under threat, or it will take the piece in question when this square is under threat, if the taking piece, so the capturing piece and the captured piece, are of equal value, or the captured piece is of greater value. And it then sends this information down here if it found a valid move. And this information then gets sent into this machine. And this white part here, this white section, all of this essentially serves as it's a lot of like instant wire logic that essentially updates the location of the pieces. So it updates the location of the pieces for the piece that actually moved. So finding the lowest value piece that can move. The source piece is less than or equal to the destination piece, or the destination square is not under threat. If it did not find a valid move, then it essentially cycles back up this tower. So if it didn't find a valid move for the destination square that it checked, then it sends another pulse up this tower, and it just kind of iterates through up this tower until it's out of pieces to check. So this is black, and that's incidentally what these light bulbs are here. The lights are essentially the destination pieces that it's cycling through. So if it has two pieces to check, the light bulbs, like, you'll be 2 or 3 lights. If it's 5 pieces to check, then it'll light up all 5 until it finds a valid move. So it cycles up this and repeats the entire process again. So it goes all the way over to pulse the next highest piece. This line might be slightly cut off here in the video, but that's where this goes back all the way over to pulse next value. If it's out of pieces to check, it then picks a random square on the board and tries to move the lowest value piece to that random square. So before I move on to that, I'll show you a couple of the interesting things I found working with all the logic up until this point here. A lot of my constraints in the difficulty or challenge in building these towers were space constraints. The machine goes from bedrock all the way to build limit. So I had a vertical constraint, and it also fills out the majority of the loaded chunks on the horizontal here. So this is the maximum chunks that I can load. And given that it's redstone, it has to be loaded at all times. Otherwise, of course, the machine breaks. And so I had a constraint in the horizontal as well. So that was probably the biggest challenge in designing these towers. The sticky piston honey block combo came in handy here. The fact that they don't interfere with each other. And one thing that I had to use frequently is this combo of blocks here. And so if you have a piston, and most people know this, but so there's 2 things that are at work here. One is when you have glass, or when you have a power flowing up blocks, but you don't want it to flow down blocks, and you can use glass to act as a diode. So in this case here, the power flows up, but it does not flow down. And over here, it flows up, that does not flow. Yeah, it doesn't flow, doesn't flow down. So that's something I had to use frequently. But what I also needed was I needed because there's so many pistons in here, essentially because these things line up right next to each other, what you end up having is when it's actually built, you've got sticky pistons, oh sorry, sticky slime blocks right here. And so I needed to have a block that allowed me to do the diode flow where electricity doesn't backflow, but also that wasn't, can't be moved by a slime block. And the only one that I know of is, for that combo is um, powdered snow. Oh, sorry, not powdered snow, but what is this called? It's just snow. So if you have snow, of course, the obsidian doesn't get pushed by a slime block, but neither does snow. And so this allows me to have a scenario where I can have, like, have redstone flowing forwards, but not backwards, and doesn't get interrupted, doesn't get broken by sticky pistons. Then another uh, trick that I used to build in all of the rules is, you'll notice I only have like one template for these towers here. So I actually have two. I have one going forwards and one going backwards. But when I construct this enormous block up here, especially when there's a bigger board, then I have to actually build in all of the rules. And so once again, I did that procedurally. It's so much easier to write in code. And in code, I would just then figure out, build an array and figure out where the valid piece moves are. And where they are not, I can just replace one of these with an air block, for instance. So these lines here, wherever there's like a pink slab, these are variables. And so it would replace whatever's on that pink slab or pink full block with an air block. And the air block essentially would then prevent the circuit from closing, which, just allowed me to quite easily script this whole thing out. I can just copy paste these to form this volume up here, this big, 3D space, and then run another set of fill commands to fill individual blocks, individual locations with air. And that way, no matter how big the board, it was pretty straightforward to iterate through all of the piece permutations or the valid piece moves. So I didn't have to manually build 64 by 64 towers for every single piece. Instead, it's all scripted. So now that it has not found a piece that it can capture, it picks a random square and checks whether that square is empty and can be moved to. And that happens at the very top of the machine. So if we go to the very top here, by now the pulse has traveled all the way up. And up here I have once again, a scalable randomizer that checks on two axes. And it uses the randomness of dispensers and shulker boxes to essentially give me a random value of redstone output measured by a comparator. And I do this twice. I have this duplicate, so there's one here, and then there is one right here. And right here we have 3, but it builds the machine with the appropriate number of shulker boxes in there. And then each shulker box has a different amount of blocks in it, so it actually gives a different comparator output. So since I do this twice, I can then multiply those values together, and I can have a random XY coordinate on the board that scales. I could go all the way to 9 by 9 because there's 9 slots, but yeah, I only need 8. And it goes into this system, and this system essentially joins those two values, the X and Y, and gives me a single output line. And the output line then gets tested against the output square gets tested against 2 variables. So it checks whether it's empty and whether it can be moved to. So the reason this empty check here is because the way I built the machine, it has already checked through or iterated through all of the opponent's pieces. So I don't need to waste time checking for checking squares that have a piece on them. And this also allows me to sidestep the issue of needing to avoid destination squares that contain a piece of your color. So if you're trying to make a white move, instead of checking whether a white piece is on the destination square, I just check whether it's empty, which was much easier to build. And that way I can be sure that it is a valid destination square, as long as the second criteria are fulfilled, which is, can it be moved to, i.e., is it a valid piece move for the piece that's moving, so that the source destination, so the source piece to the destination square, and is there any collision like detection that needs to be accounted for. And once again, because this machine is stateful, and I'm not certain I'm using the right terminology there, but because these values are held in a constant state, I don't need to pulse through these checks. I already know where there's power being held here, which squares are empty and which squares have valid piece moves or are valid piece moves from the source square. So then I ran into an interesting issue. If we go down here, and you look at this board, this is only a small board, so it wouldn't be as much of a problem here. But once this scales up, the way I iterate, or the way I numbered the squares, was going from left to right and then looping back down to the next row. So this would be square 1, 2, 3, 4, 5, 6. So say I pick a random square and it's not a valid move, then I just count up 1 and I say, okay, check the next square. So instead of cycling through and picking new random numbers each time, I found that it would be easier to, or much quicker, to just then cycle through all the subsequent squares after the one that was picked randomly. The problem is, when you cycle through squares this way, you end up having a skew towards the top left corner. You can imagine with your white pieces in the bottom here and the black pieces in the top, it's very rare that it will randomly pick a piece that a white or pick a square that a white piece can move to on the first try. What's much more common is that it would pick a square either where there's already a black square occupying it, or a black piece occupying it, or a square where there's a white piece occupying it. And then it just cycles through until it finds the next available square. So once it gets to the end here, it loops back to number 1, keeps cycling. And so what would end up happening is most random moves for white especially, but also for black, would skew left and top. And so I didn't get a good random distribution of moves. And so what I did instead is I built in another, like, a component of the machine that rotates this entire board by 90 degrees. So just for the randomizer, I then, instead of iterating like this, 1, 2, 3, 4, I rotate it by 90 degrees. So then I go 1, 2, 3, 4, 5, 6. And this allows me to get a more even random move distribution. And so that is this very top part here. What you see here, the orange and yellow lines. And just kind of annoying to build because it needed to be built because lack of foresight on my part on how I kind of decided to iterate through the squares or to count the squares. But it did make the games just much more, the random moves seem much more random. And so I feel like it was worthwhile building in. So once again, the challenge with a lot of this was building things that I could then scale easily. So if you look at this randomizer, it's fairly small because once again, we have 9 lines. But once you have an 8x8 board and you're talking 4,000 of these rows, this randomizer scales, like needs to scale much bigger as well. And on top of that, everything having to be instant wire, it just makes the machine a lot bigger than it could be built much more compact. But I wasn't going for compact. I was trying to go for speed and playability. And I think what I came up with is, I think a pretty good version of that. Okay, so now we have found a valid move, and we now tell the machine to move the piece. This gets us to the next section here. Because I've been sending the source destination squares that I'm checking through, I've been sending that to the machine, to this other part of the machine, as I iterate through the destination squares I'm checking. That means that I don't have to resend any of that information. And instead, once I have found a valid move, I can simply pulse that piece to move, and it will know which destination square it needs to move to because that's already been sent to the machine. And so the piece then moves to that destination square, and it also clears the opponent's destination square. If there's nothing in that destination square, great. But if there is a piece, an opponent's piece in that square, then it gets cleared because it's now been captured. And all of that happens, like I briefly mentioned before, in this white section here. So this white section receives a signal from this control tower up here, that it's found a valid source square, that gets sent here, or actually it finds a valid source piece, and that gets sent here, and that piece then moves to the destination square that's been locked in to this machine, and it also sends a signal over to the other side to clear that destination square on the opponent's side. So now we have successfully moved a piece to the new square. We have cleared the value from that previous source square. So the move here it clears the source square and then updates the destination square for the piece it's moving and clears the opponent's destination square. So this is the data part where it's actually storing the information. But I have to send that to the board as well. And so as it's doing this data storage or data update, it also sends the source and destination squares to the board controller. So the board update requires a couple of pieces of information. It needs to know the source piece and the destination piece. Or if the destination square is empty, it needs to know the source piece and the fact that the destination square is empty. So I guess what it really needs is it needs to know what is occupying the source square and what is occupying the destination square. And so with those 4 pieces of information, so destination square, source square, what's occupying the source square, what's occupying the destination square, it sends all of that to the board. And once the board controller has all of that information, it then launches through a piston sequence cycle that updates the board appropriately. And a lot of that happens down here underneath these main machines. The board controller is this piece over here. Once again, this scales out. So I think after this, I'll show a bigger board and I'll kind of show how all of this scales. So this board controller waits for those pieces of information. And when it has that information, it then launches into action and essentially sends out information to several parts of this board here. So this board was difficult to design, to say the least, because of how tight everything is. I wanted to make it as compact as possible. And so you'll notice that the pieces here are slightly offset. Each square is actually 5 by 5 blocks wide, versus the pieces are only 2 by 2. And that's because the sides of the individual squares actually interlace with each other because of the amount of pistons that are required. And the way I did the vertical data transmission for a lot of this was, you can see here, is essentially pulsing these piston lines. It allows me to make very compact vertical data transmission. And then here, this looks like a convoluted mess, but what it is a bunch of observers that direct the pulses that come from this square panel here into the appropriate pistons that make up each individual square. And then on the controller side here, you'll notice I have water columns. So one thing I do is I send a pulse from the bottom here, just soul send, and this vertical update can be measured. It happens after a delay, but the delay is consistent. I think it's 2.8 seconds for removing the soul send, and it's shorter for the other one. It's like 1.2 or something like that. But I can read that change in the bubble column with observers. And I needed something that, once again, passes the information vertically simultaneously to every single layer. So this way there's no delay, and I can house this entire thing in pretty much a 1-by-1 block vertical column. So there's this data that's coming in from the controller that controls which x-axis to update on the board. And then there's this side here, which controls which y-axis to update on the board. And essentially that allows me to send power to an x and a y coordinate system, which will only denote a single square. So if I send it to 2, 2, then any updates that get sent through this machine here only go to update the pistons responsible for this particular square. So this section right here then sends the piston sequences up the machine to all the layers. And here it makes a right-hand turn. So the data comes down from here, goes up, it's over, and then it gets sent down these lines here. And the combination of that allowed me to have one data line, which sends any piston sequence to any square in this board. And I control which squares actually receive that data by having the X and Y selector lines. So the data line here always transmits the piston sequence, and that information can be transmitted to any single square on this board, depending on which X and Y coordinate line I'm holding power to. Okay, so we jumped ahead a bit here. So we're now in this section and updating the board. So the board controller gets pulsed, and it first clears the source square, and then it gets pulsed again, and then changes the destination square. And after all of that is done, if the lever is flipped instead of just a button pressed, then it starts the next process, the next move. So for this part here, what I found was if we look at one of these, just to give you an idea on like the amount of piston sequences that I needed to account for. Let's go over here. Here's a layered version of this. So this is one square. And so you'll notice here the square is actually 6 by 6 wide. And this is what I meant with the interlacing. So I built this in a way that they could interlace in a 5 by 5 pattern. So wherever there's like this line of the next square fills in this block right here, or this section right here. So I had to build it that they don't interfere. And the amount of pistons that I need to control are essentially one piston per observer here. We go over here. Let's see if she'll do this differently. We get rid of these blocks. And so here now you see all of the different pistons that need to be controlled by these different observer lines. And so in order to make the changes, I needed to fire these surrounding pistons in a certain sequence to move from, let's say, a black pawn to a white queen. And I had to do that for every combination of pieces. Because when you're moving, there's two squares that are being updated. The source square goes from occupying piece to clear. And then the destination square goes from occupying piece to the piece that was on the source square. If the destination square is empty, then it goes from clear to whatever piece was here. But if the destination square is occupied and it's a capture, then I can either clear that square first, and then run another piston sequence to now occupy it, which would allow my basically the amount of piston sequences that I need to consider to be much fewer, because there are 2, 3, 4, 5, 6. There are 6 different piece types times 2 colors. And if you add clear into that, there's 7, clear square. So I would essentially have to do, what's that, 14 different combinations in both directions. So that's from clear to new piece, or from new piece to clear. I don't think I explained that very well, but I didn't end up doing that. What I ended up doing is figuring out the piston sequence to change the current square state from any piece to any piece, or at least from any piece of one color to any piece of the other color. And the reason is speed, because if I have a piston sequence that changes the layout from black pawn to white queen, that's going to be faster than going from black pawn to clear to white queen. This, however, meant that I had to find a pretty big number of different piston sequences, and that's what's stored in this big section here. And what this machine does is, once it knows what source piece and destination piece values are, so what the square, like the change needs to be on that square, once it knows that, it sends the information down these lines here, and it sends it into the appropriate vertical stack. And then that pulse gets sent down these lines, and the returning data gets sent back up here to actually do the piston sequences. So essentially you see a pulse going down these lines, and then as the pulse goes down, there's a bunch of pulses being sent back up the other way. And I had to split that data so that it gets sent to every possible square on the machine. So what I had to do here is right here, this big section, this essentially takes any data coming from any one of these lines. So each one of these is a horizontal slice, and it will then move it all the way up and compact the data here, send it out these 5 lines, and this goes back into this control tower, or into this tower, this data tower here, that then sends all this information vertically, and then it does this 90-degree bend and finally arrives at every possible square for the board. It's a bit hard to explain all of this, as you can tell. I do hope that that you guys find it interesting, and yeah, I'm happy to answer any other questions. But I know with projects like these, it's uh, yeah, I think it's more like interesting to kind of understand a little bit of the logic behind it. But I'm definitely not going into like all of the detail here, and I find myself getting lost in my own explanations already. So, but that's kind of how the machine works. It it checks which pieces of the opponent it can take. If it can't take any, it picks a random square. It makes the update in its own storage, and then the board essentially has to fire a specific piston sequence twice, for the source square and for the destination square, in order to reflect that change on the board. I think there's something like it's either 10 or 100 million different piston sequence permutations. And so to find the optimal sequence for every um, change, every piece change, I wrote another program which basically, yeah, figured that out for me. And it would um, like that's a kind of a whole nother um, yeah, uh, whole nother interesting side project. It took a while to kind of figure this out uh, because of the number of permutations. I couldn't brute force it, so I had to use a couple of tricks to to figure out what the perfect piston sequences are. But what I ended up with was the shortest or the least amount of piston firings required to change from any piece to any piece with the piston layout that I have here for these squares. Yeah, some of the other interesting things that I work with. So I have the walls for instant downward transmission that I use in several areas. This one here, I think is pretty cool. This will send a pulse down instantly. So it has a delay, but then the delay is identical no matter how high the tower is. So you'll notice that when I push the button, nothing happens. And then when it pulls up, they all pulse up. And something interesting I noticed is after you get to a certain height, it just stops working. So you'll notice here I have this kind of repeating pattern of redstone block, note block, piston. But at this height, I had to add an observer layer. So this makes this ever so slightly smaller, or sorry, ever so slightly take ever so slightly longer. But yeah, starting at a certain height, like for some reason these pistons just stop transmitting that pulse, and so I just had to throw in this observer layer here. And I think it was only for I had to do it for these three. So the 8x8, 7x7, and 6x6, they were just too tall. Yeah, these are the repeating storage uh, elements that store the piston sequences. And so once again, it's built in a way that I can just copy paste this out, thousands of times, and then I run another program that actually fills in, like adds blocks here and puts a redstone wire up here so that when this moves down, this gets powered. And this all works on zero tick repeaters as well. There's a lot of zero ticking going on, a lot of instant wire. Yeah, this here is the vertical data transmission for the board. And then here is the right angle that it does. Some of these components I don't end up using. I think as I was iterating through this, like I tried to clear out the pieces that I wasn't end up using, but I think every now and then I missed a piece or two. But for the most part, every piece you see here on this polished diorite is being used in the machine to build. So yeah, that is in a nutshell how this machine works. So yeah, that is in a nutshell how this machine works. Um, yeah, I'm unfortunately out of time here, so I'm not going to load up another board here right now. But once again, you can download this map in my previous video. It's in the description, and you can play with it yourself. And I also explain, I think, in a pinned comment, how you can build this machine with the data packs that I have on this map. So yeah, thank you for watching. I appreciate it. I hope you enjoyed hearing me ramble for all this time. As I mentioned, I'm working on another project that I'm excited about, and I hope to post that very soon. So thank you all for the comments and feedback. And uh, yeah, I hope to see you all again in the next video in a few months. All right, take care. Bye.